Welcome to the Discover Alaska Lecture Series, brought to you by UAF's Summer Sessions and Lifelong Learning. My name is Althea St. Martin, and I'm your host for this summer season. Summer Sessions once again has a full lineup of free programs Monday through Thursday evenings at 7 p.m. Tomorrow night, Thursday, Music in the Garden will feature Emily Anderson, and that's going to be at the Georgeson Botanical Garden. Then on Monday, the Author's Corner will feature the book "I Thought There Would Be More Wolves" by author Sarah Ryan. And Tuesday, the Healthy Living series will feature Dr. Pete Dillon with Family Medicine at Tanana Valley Clinic. His topic will be methamphetamines, lessons learned from the medical perspective. Each Wednesday night over the course of the summer, Discover Alaska features a local community member speaking on a wide range of Alaskan topics. We appreciate the time that they are donating to help us all learn more about our great state. Next week on Discover Alaska, we'll hear from Stan Justice on where did our trails come from. The Discover Alaska series is now in its 16th season, and this year the in-person programs are held in the BP Design Theater located in UAF's new engineering building. It is also live streamed and recorded. This allows us to take advantage of technology to present to a much wider audience. You can review and share all of the Summer Sessions lecture series later by going to UAF Summer Sessions website, and that's at uaf.edu/summer/events. Tonight, in addition to questions from our in-person audience, our online viewers can type questions for the presenter into the link at the bottom of your screen or the chat box at any time. But before I introduce tonight's speaker, a few housekeeping items. Please turn off your cell phones. And also, UAF's mask policy is you do not need to wear a mask if you have been fully vaccinated. And tonight, I am truly delighted to introduce the speaker, Mark Johnson, who is a professor at UAF's College of Fisheries and Ocean Science. He has been with UAF since 1990, and his research is based on Arctic climate variabilities. His topic tonight, opening of the Arctic for shipping and resource extraction, and the role Alaska will play. Please help me welcome Mark Johnson.
Thanks, Althea. Welcome, everybody. So tonight I'll talk about the way the Arctic is going to open, at least the way I see over the next decades. I'll be presenting current research from my own lab and from others in Alaska as well as around the world. I'm a professor of oceanography, and there's several disciplines in oceanography. You can be a biologist and study fish and the things that grow in the sea. You can look at ocean chemistry, the way carbon dioxide goes into the water system. You can do ocean physics, which is what I do, which is to ask how does the ocean move around the planet. That's important for climate change because the heat on this Earth is moved around by the oceans. So if you want to know where the heat goes, you study where the oceans go. So I'm a physical oceanographer in the College of Fisheries and Ocean Sciences. In the lower left of your screen here, you see two pictures from the research I'm currently doing up in Barrow, Utqiagvik. And we're putting sensors out on the sea ice. And those sensors measure the sea ice motion. And they tell us, we're trying to figure out if they tell us, how the ice will break up, when it will break up and go away. And that's important because if you know when it's going to go away, it will tell you something about when you can start having ships up in the Arctic Ocean. And in the right-hand side of your screen, if you're not used to looking at the globe in this fashion, let me try to orient you with the picture that you see. There's Greenland there at about the 7 o'clock position. It's covered with ice. And on the top of your screen is Bering Strait, Alaska, Russia, right there. And it's good to have that orientation. Most of us don't look at the globe that way necessarily. A little orientation will help. This is the same picture, but now we can see the two sea routes that I think are going to be important for this discussion. We can see the Northwest Passage. It's running along west of Greenland and through the Canadian Archipelago, those islands that are west of Greenland, along the coast of Alaska and out Bering Strait. There's the Northeast Passage, which is along Norway and Russia. And you can see where Norway is down around 5 o'clock. Russia here is all along the right-hand side. And that also helps you get oriented. I also want to point out where the Canadian Archipelago is. There's multiple routes through it. You've seen where Bering Strait is. Spitsbergen is, if the pointer works, is here. That's Svalbard today. That's going to be important for this discussion. Franz Josef Land is here. That's important because in some of the work that was done by our early explorers, they wound up going to Franz Josef Land. Wrangel Island is here, and we're going to revisit that with one of the expeditions. So that's the map that we'll use. We'll use different variations of this throughout this talk. Here's what I'm going to tell you about today. I want to go back to 330 BC when the first person sailed up to Norway and observed this ice-covered ocean. I'll not do a complete history, of course, and we'll touch on John Ross and Edward Parry from England, who did explorations in the Canadian Archipelago. We'll talk about this idea of the open polar sea, that in the mid-1800s, the idea that the Arctic was ice-free. That led to studies and work by DeLong and Nansen and Amundsen, who are names that you should have if you are interested in the Arctic. And then we'll talk about the Arctic opening up and why there might be an ice-free Arctic in the summertime. That's based on the CO2 increasing and how that varies with temperature. It's a short version of the global change story. And that means that there's loss of sea ice, loss of the older ice in the Arctic, and a lengthening of the open water season. The open water season is the season when you can drive vessels around the Arctic, when you have access to open water. If all this happens, what are we going to have to deal with? There will be geopolitical issues because there are competing interests in the Arctic and there are overlapping claims. These will have to be sorted out. I won't go into a lot of detail. That's far beyond what the studies I do. There'll be better access to oil, gas, and minerals. These are resources that we will wind up extracting at some point in time. And if you have a smartphone, you use rare earth minerals to make your smartphone work. An open Arctic means there's shorter, faster shipping lanes. Going across the top is much better than going south. Shorter telecommunications, they're already putting and have put in fiber optic cables. If you're a stock trader and you can trade more quickly, that leads to dollars, so there's economic pressure to put in cables and improve telecommunications. But it has some challenges that I'll go into. I'm going to talk about the icebreakers that we have in the United States. We're woefully behind other Arctic nations, and I'll give you some details on that. There should be a deep water port at Nome. Money's been allocated for that. What does that mean if there's a deep water port and ships are coming to it? What do you need for infrastructure? There's costs that are associated with that. And all of these advantages to an open Arctic mean that we're going to have to do better at forecasting sea ice and the sea state for navigation in this operational window that'll happen during the summertime. And if we get those forecasts wrong, that's going to cost money and it might cost lives. And I'll close with a few recommendations for the future. Let's go back to 330 BC. Pytheas was in Europe and he crossed the landmass because the Straits of Gibraltar were closed to shipping because of the geopolitics of that time. And he went up to Thule, which is in Norway. And he described in the middle paragraph that they're a sluggish sea where there is no separation of sea, land, and air. If you've been to the Arctic, you know that it can white out and you can't tell land from ocean. And he found a mixture of this jelly-like stuff that he said you couldn't sail through it, you couldn't do things on it. And this is a reference to, in the Nupiat language, kinu. It's slush ice. We've all had a Slurpee at 7-Eleven, that stuff that's just slush ice. That's the first ice that forms before it turns into solid ice, but you can't drive an outboard engine through it. It doesn't come up to cool the engine. So If you're doing search and rescue at this time of the year, you can't have an outboard engine. So he was the first one to actually see that there was a midnight sun. There's lots of other history that happened, of course, but I'm going to jump to the 1800s when England was trying to find a way across the top. Sir John Ross was sent to explore Baffin Bay. Baffin Bay is that body of water that's west of Greenland. And he was sent there with second in command, William Edward Parry. And so Ross took his vessel and they cruised around Baffin Bay and they charted it and they did all the things that they were supposed to do. And they went into Lancaster Sound. You can see that it's marked there. And they went west. And the leader, John Ross, said, well, we can't go any farther. You see those mountains in the distance? Time to go back. And his second in command, Edward Parry, said, no, 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 I don't think so. Look, there's a sea state that's coming through from the west. We have breakers and rollers that are coming through that can't be mountains. So when they got back to England, he convinced the Admiralty to send another expedition and he was going to push on farther. And other things happened to John Ross because of this bad decision, but that's another lecture. In part of his studies through Baffin Bay, he discovered the northern people, the Arctic Highlanders, and that's a site of active archaeological digging to this day up in Etah. So the mid-1800s come along and there's this idea that the Arctic Ocean, which is unexplored at this time, is an open polar sea. And the idea was that the Gulf Stream that's coming up through the Atlantic along Norway has so much heat that that heat's going to melt away the Arctic ice. And the Kuroshio that's doing similar things is coming up and bringing heat. And that if you went to the Arctic Ocean, once you got past this rim of ice, you would have an open polar sea and you could sail around it and do all kinds of things. It's a great theory because, in fact, the Gulf Stream carries an awful lot of heat up into the Arctic Ocean, and there is enough heat that it carries to melt all the ice. But we know today that that Atlantic water is so saline, so salty, that it's kept at depth. So it's insulated from melting the sea ice. But it's a question that we're actively looking at today because if we can mix that deep, warm Atlantic water up to the surface, it will exacerbate this idea of an opening Arctic. So to test this theory, George DeLong left San Francisco in the Jeannette, came up through Bering Strait, west of Wrangel Island to about this point here, north of Siberia, and his ship got trapped in the ice. It was crushed. The men had to survive by trying to get to the landmass. Most perished. It's a great adventure to read about in the comfort of your own home, but is a real tough tale of survival. And so that ship was crushed up in the Arctic ice. And several years later, remnants of it were found here off the tip of Greenland. So a guy named Nansen said, hey, that must mean that the currents in the Arctic Ocean must go from this Bering Strait side out this side. It must go in that direction. So Nansen said, I want to test that idea. So Nansen built a special boat. That boat was designed so the hull could withstand the pressure of ice compressing it, and instead of breaking the hull, it would lift it up. And so Nansen left with his crew, went up along the coast of Russia here into the Laptev Sea and froze the Fram into the ice, and it drifted across the Arctic Ocean. And they wanted to get to the pole, so he and a colleague scrambled on the ice as men with sledges trying to reach the North Pole, abandoned that idea, and wound up overwintering in Franz Josef Land, and it's another great tale of survival. But the drift of this Fram is a classic oceanography story because it also shows the current pattern of the Arctic Ocean. And if you want some good reading, Nansen's The Farthest North is a great book to read. His observations of the way the wind blows on sea ice have led to some classic textbook cases that we teach in oceanography on something called the Ekman spiral, which means that when the wind blows this way, if the wind is blowing at my back going this way, the water column below it winds up going that way because we're on this rotating planet. And we thank Nansen and one of his students, Ekman, for that. The Northwest Passage in early 1900, Amundsen found a way through that on the Yoa, another great story of trying to find a way across the top. You can go to your browser and Google the Yoa and find several great YouTube videos that'll show you the people he met and what he did. So now we have kind of a cursory coverage of how did we figure out that there might be a way across the Arctic? How did these ideas of a Northwest Passage come to be? And they came to be by the people I've just described. So why is this Arctic opening? Why is it an ice-free Arctic? So put on your global change hats, because here's carbon dioxide over the last 800,000 years. You can see it's varied around 250 ppm. And now recently it's gone up to here. And let's blow up the recent times, and we can see now here it's up to 420. So when people say, oh no, carbon dioxide was really high long ago, you can say, yeah, well, 800,000 years ago it was never this high. And it's changing more rapidly than we've ever seen it change before. So this is uncontested. This is fact. This is also fact that temperature and carbon dioxide vary. And there are some people who will argue, well, when the temperature goes up, it drives the CO2 up, and there might be a school of thought for that, but the larger body of evidence suggests that when you increase CO2, temperature goes up. So here it is going hand in hand. And now this high blue CO2 going up to here is raising the temperatures of the globe. So how does this work? We're on this neat planet that has a sun. That sun is 4,000 degrees or so Kelvin, and it's radiating light. That's the light that our eyes have adapted to see. That's why I can see you and you can see these slides. And that radiation comes in here, and it puts the Earth at a certain temperature. That temperature is not the temperature of the sun, it's a different temperature, so it radiates differently. Just like when you put a poker in the fireplace and it gets red hot, it's radiating at a certain temperature. If you get it to be white hot, it's radiating at a different temperature. That means the spectrum that the sun is radiating and the Earth is radiating are different. So that's what this slide is telling us. Here are a bunch of wavelengths of energy, of light. It doesn't really matter what they are, because here's what this is telling you. The sunlight at the top of the atmosphere follows this curve, this black line here, gets to the surface of the Earth. Now the Earth is some temperature, much cooler than the sun. It's radiating back. And as it radiates back, water and carbon dioxide trap some of that energy that's radiating back. It's simple physics. There are basic physical equations that describe this. If you increase the CO2, you trap the energy. That's a fact. So we add more CO2 and we trap more energy. That's how it works. So if that's true, the Earth should be warming. And it is. Let's go back to 1860. Let's take all the thermometers that people have had in this world everywhere, and let's discard the ones that have problems. Let's do other stuff to them to kind of say, don't like that one, don't believe that one. We'll do a bunch of science. And we can see that the temperature globally has gone up. And you might say, well, wait a minute, that line is sitting over here at 0. That's because I've taken away the mean temperature. So if I relabeled this graph and just put the mean temperature here, that would be fine. So this is what's called an anomaly. I've taken out the mean, but the trend is there. I can move this graph up and down to whatever the mean temperature is. Well, that's just the atmosphere, and there's all kinds of problems. There's heat island effects and things like that. What about the oceans? Let's take all our measurements that we take from the oceans. How do we do that? We go to sea in ships and we drop instruments into the ocean and record temperatures, and we add all those temperatures up and multiply them times the volume of water that we measured, and we get a heat content, right? If this room is filled full of water at a certain temperature, it has a certain heat content. If I have a glass of water with that same temperature, it has a smaller heat content. So let's do that. We can see the temperature of the southern hemisphere is increasing, the northern hemisphere, and both of those together have undeniable warming trends going back to 1945. The atmosphere and the ocean of this planet are warming up. So when I talk about things like this, not to colleagues, but over beers with friends or skeptics, they'll say, well, there's no global warming, it's all the natural variability of the Earth. And what I say is, no, it's not natural variability, it's basic physics. And those equations that describe the way CO2 absorbs the radiation that this planet is giving off proves it. It's undeniable, it's basic physics. Then you might say, well, okay, what about all the models that are trying to forecast the future? Here on the lower right is natural forcing only. Let's take observations. That's the dark line that's going up to here. And let's run these numerical models. And yeah, they're tough to code. It takes some really smart people to figure out how to do that. And let's run those models, but let's not include the heavy CO2 load. We can find that the results of those models don't show the real warming. But when I put those anthropogenic signals into my models, I get a match. That's pretty strong evidence that things are going in that right direction. Basic physics, if you include CO2 in the models, you get this warming. So what's that doing to sea ice and the open water season? Here's 1984. Here's Greenland, we recall. Here's the Canadian archipelago. Here's Alaska. And the white is the sea ice extent. The extent is the measure of how big is the pancake. The pancake of ice in the Arctic Ocean, how big is it? Did I make a big pancake or do I have a small one? In 84, here's how big it was. In 2019, it's reduced. Maybe that's natural variability, maybe not. That's only 2 data points. Let's take all the data points from 1979 to the present and measure that extent, that area of the pancake, and it's going down. That's a pretty strong trend, I believe it. Let's look at the 2 years that I've marked here in red and in blue. Here's the record minimum we've seen so far. It looks like this. Here's the mean ice in the summertime, this red line. In 2012, it was reduced to that. In 2016, it was reduced to this. The pancake of ice in the Arctic Ocean is shrinking. It's pulling away from the edges. It's shrinking towards the Canadian archipelago, towards north of Greenland. So we see this. Why does this record start in 1979? Because this is the satellite records. Satellite records started in the late 70s. It was too difficult to measure the size of the ice sheet before we had satellites. So what about the annual cycle? So here is May through September, and this is the extent, the size of the pie on the y-axis. And the dark line at the top is the way the ice behaves on average. It starts off in April, May at this amount here, and it decreases to September where it gets a minimum, and then it goes up. That's the standard cycle. By the time September rolls around, the warmth from the sun has warmed the ocean, and the ice is at a minimum in September. Not June like you might expect, but in September. That's what happens. That's what's been happening. If we look at individual years, here they are, 2011, 12, 13, 14, 15, you can see that we're less than the average and we're really getting less in September. All the evidence is pointing towards this loss of sea ice. The age of this ice is also getting younger. Before man came around, ice would melt in the summer, but not all of it. And the ice that didn't melt that summer froze and got thicker the following winter. and then didn't melt the next summer and froze the following year. So on average, there was ice that was older than 8-9 years, and it sat here up against the Greenland Canadian side of the ocean. Old, thick ice. That's what the whalers use for fresh water, because as ice gets older, it pushes out the salt from salt water. You can drink it, it's potable. They look for old ice and they melt it. That's their drinking water. But as in 2008, most of that ice is gone. It's either melted or it's left the Arctic. Remember the Fram and the Jeanette coming down here out of Greenland? This older ice is departing the Arctic, and by the time it comes down here, it melts away. So the Arctic is changing. So now what do we do about it? Well, if you're Denmark, Russia, USA, or Canada, these countries here, you've got claims in the middle, and some of those overlap. So the leaders of the world, Putin, Biden, others to come perhaps, they're going to have to sort this out. And I just point this out because this is an issue that has to be addressed, but not by me. This area here, the Arctic Ocean, this arena is going to be, it is complex and it is unpredictable as far as what's going to happen. There will be conflicts that are on the land, in the air, on the sea surface, and under the Arctic Ocean and under that ice cover. And we've all seen great YouTube videos of subs coming up through the ice and all that kind of stuff. Some of the work I do, we get to put instruments at those experiments that the Navy's doing, and it's just really fun, interesting stuff. This arena is going to be fascinating to watch. Why do we argue over who has what? We do that because there's undiscovered oil and there's undiscovered gas. Now, of course, you might ask, how can you show a plot of undiscovered stuff? I don't really know. But the US Geological Survey says this is their best guess. So without drilling into the detail here, I take away from this that there's lots of it there, there's lots in the Arctic Ocean, and people will want to get it and use it for energy and make money and do all that kind of stuff that people do when there's gas and oil to be had. Who has it? Here are the amounts of available gas and oil for US, Canada, Russia, Greenland, and Norway. Russia by far has access to most of the gas. Then the US, Canada, Greenland, and Norway kind of about the same. So this will spark some competition. And it means that if we're out there trying to get gas, and I say we humans, then we have to figure out, how do we do this safely? How do we do this without changing the environment up there? How do we not have a deep water horizon in the Arctic Ocean? Where are the ships going now? Here's our polar projection, and here's two pictures showing the same thing. Where do the ships go? They skirt the ice of the Arctic Ocean and they stay around the edges. And they go through the Canadian archipelago a little bit. And then you might say, well, who's doing this kind of a pattern here? And who's driving a ship? What crazy person is driving a ship like that? Those are all scientific expeditions where they're trying to map stuff out. You can recognize the grid pattern that scientists think in. We want to measure things in X, Y space, and so we drive grids. Same thing over here. There's ships that are coming up into the Arctic here to Svalbard and along the coast of Russia and coming out through here. This pinch point here in Bering Strait will become important as more and more ships go through that place. Who's going through there and how often are they going through there? Here's this map that we're now familiar with on what the routes are, and note that in the future sometime, don't know when that'll be, maybe we'll just drive straight across, right through, right down the middle. Don't know when that'll be. Right now we're going to hug the edges. Here's a plot of the number of ships that have gone through the Northwest Passage all the way up to 2004. It's increasing, but most of those are small vessels, adventurers, people who want to kind of go up to the Arctic and see what it's like. And this quote here by Christian Haas, one of my colleagues, he's a Canadian, commercial traffic hasn't really increased in the Northwest Passage at all at this time. Why not? If everything I'm saying is true, how come there's not way more ships going through there? Because we really can't do it reliably. We don't know exactly when we can drive a ship through there right now. It's not routine enough to bet your shipping company on this today, but it will be soon. So I've talked about the geopolitical issues, the better access, shorter, faster shipping lanes. Let's touch on telecommunications, icebreakers, and a deep water port and forecasting. Here's the global cable pattern. Of course, Europe, New York, London, wow, there's just lots of traffic here. That's your internet. That's your WhatsApp talking to your buddy in Portugal. That's the line you're using. Well, one of those, there's lots of them, thank goodness. What do? They're internet and telecommunications. There's over 1 million kilometers circling the globe. How do they do that? They have special ships, they go out, they just unspool a big cable, and they're good to go. It's not that simple, of course, but that's basically the idea. Now, this must mean that sometimes these cables break. So it means in ports here, along the west coast, along the east coast, all over the place, you have to have ports with vessels ready to go at a moment's notice to go fix something, because there's billions of dollars at stake if those cables break. So there are vessels that are ready, guys sitting around just like your local fire department, guys who are ready, men and women who are ready to go out and fix these cables. What about up here in the Arctic? Phase 3 coming to the Arctic Ocean. Phase 1, I'm going to talk to you a little bit more about this. This is already in place. Runs from Prudhoe around across the top, Point Hope through here. Phase 2 will hook us up over here with Japan. Phase 3 will connect us with London. It's happening now. There are plans to do this. This phase is already done. Here's the timetable. You put in a cable, it's a shorter transmission time. Plus it adds to the redundancy. And I'll talk about why redundancy is important in a moment. Here's the close-up of this phase 1. Going through Fairbanks. We are the hub of Alaska. No matter what's happening in Alaska, it's going through Fairbanks. Road to Nome, it's going through Fairbanks. Cables, going through Fairbanks. That's kind of comforting to know. This cable is in place, it runs off here. What are the things they have to think about when they do this? In the wintertime, there are big chunks of ice that want to grind through and run ashore and dig down into the bottom of the ocean in the shallow parts. So these cables have to be buried well below the depth that the scouring of the ice will reach. And they've figured all that stuff out, and they know how to do it. So these cables are important. They're important to telecommunications, they're important to internet, they're important to the way we live our modern life with our cell phones. So here's the ultimate hybrid strategy for warfare in the future. You just start cutting these cables. And the UK's top military officer has already warned that Russia, somebody, rogue state, who knows, it's possible that you could deal a catastrophic blow to the global economy by just sending a vessel out there, your own private submarine that goes out there and starts cutting those cables. So if they're going to do that, how do we deal with that? It's the Navy's kind of bailiwick to figure that out. And it also means that here's Orange Marine. That's a company that lays cables and repairs them. Ships ready to sail within 24 hours. They have fleets around the world that are just sitting there ready to go. Guys who are ready to go out there and fix these cables. That's a lot of infrastructure. It's a lot of cost to have the convenience of dialing your buddy over in London whenever you feel like it. Ships have to be at the ready. Repair people have to be at the ready. It takes considerable resources to do that. What happens if there's a break in January or February in the winter? We know what it's like in Fairbanks. In the high Arctic, it's dark too, it's cold, there's an ice cover. Do we just say, well, tough? I don't know the answer to that. But it will involve more icebreakers, vessels that are capable of going out there. And both our senators happily are really pushing for icebreakers. Here's the Healy, the most recent one. It's kind of doing double duty as a Coast Guard vessel and as a science vessel. I've done work on a Coast Guard icebreaker, and it's unlike doing something on a dedicated science vessel. It's a little more difficult because there is a chain of command that makes it hard. And it's great to have a vessel that's kind of there at your command, and icebreakers are one way to do it, but dedicated science vessels are terrific. And here's the Canadian icebreaker. So Russia has 53 icebreakers and Canada has 7, and we have fewer than that. So look at this picture here. Russia has 46. That's the latest number as of 2017. And unfortunately, the little note thing at the top of the screen is showing, the header to that points you to several of those vessels. These large vessels here, these are huge. They're the Yamal and the Pobody displace 25,000 tons. That's a very large vessel. Vessels that are in the planning are these leader class vessels, 33,000 tons. One that's planned by Russia, 69,000 tons. These are the futuristic, almost fantastical vessels, somebody said. $1.7 billion each. These are not tiny toys. They're going to take a lot of muscle by the powers that be to have a budget that's going to build 1 or 2 or 5 of these. But these will break 11 feet of ice and cope with the worst the Arctic can throw. So that means these are the vessels you need to go out there in January and February. So here are all the Russian icebreakers, and not all of them are these big giant vessels that are going to go out and move ice out of the way. The Fedorov is used for some research. The Ob here is used for some research. So they're not all these massive Russian icebreakers. Oh, a lot of blank space there, Canada and the US. Canada has 7. Here's the US. 5 and 3-year plan. The Polar Sea and the Polar Star. Oh, when were they built? The late 70s and retrofitted in the early 2000s. They're not cutting it compared to those other ones. The Healy in 2000, the Nathaniel Palmer services the Ross Sea and McMurdo down in Antarctica. Boy, we got to get with it here if we're going to be an Arctic nation. President Trump called for a ready, capable, and available fleet to enhance our polar security, giving us a strong presence. I don't know what's going to happen to that now, but if Russia is building 8,000-ton ships that are carrying guns and cruise missiles up in the Arctic, the US currently is going to lease some icebreakers. When you lease something, you pay someone else to learn how to do it. They might be nuclear powered, and they're shifting from science to defense and economic activity. So that's an interesting direction. For science, it's not a great direction. Maybe for geopolitics, it's a good direction. I'll be very interested to see where the quest for icebreakers go in this country over the years ahead. Do we get in the game and say we're an Arctic country, Alaska is an Arctic state, or do we go home? One good sign is money for a port enhancement in Nome. Here's the current port, here's the future port. They've extended from this out to here so big ships can come in, cruise ships, tourist industry. That might mean that there's going to be a tourist industry all along the north slope of Alaska, big cruise ships coming in and out. If you've been on a cruise ship, you know what it's like. You get off it, you go to the port, and people are spending money and tourism and all that kind of stuff. Well, that's one port for all of Alaska. Now, where are the deep water ports around the world? There's lots of them. Where could you put them in Alaska? Here's Nome. Here are other sites that were considered by this group that considered that. Deep water ports mean that they're 30 feet deep or deeper so they can handle a large vessel. That's not free. The Port of Tacoma is spending $60 million per year to upgrade their facilities. Put that in the governor's budget or the federal budget. Tacoma has spent $1 billion on dredging. And we could go into the details of dredging, but dredging every other year or something like that is not a small operation. So what are we going to do? Now, if this is a deep water port, and there's deep water ports in the US, Charleston is a good one, Virginia, Baltimore, Miami have all of them. Are any of these cities, let's see, are there roads that go to these ports in Virginia, Baltimore, and Miami? You bet. So if you've got big vessels coming into Nome, how do you get stuff there? Does that mean you're bringing everything in by boat and taking it out by boat? I think not. We have to have a road. We have to have a road system. How do you forecast all this stuff? There's lots of academic papers that say, oh, we need more polar observations. Of course, that's what scientists do. We need more data. Give me more data. I'll write a proposal and pay me to collect more data. What might we do up here in the Arctic? Maybe we'll have a facility run by NOAA. Here's the Great Lakes Environmental Research Laboratory. Those are the people that forecast what's going on in the Great Lakes so ships can go across there. We need something like that. We need something like that to tell the ships where to go, to help for search and rescue, to say when you should go and when you shouldn't go. How good are those models? This plot here is the error in predicting the ice edge. What's the ice edge? The ice edge is the place where, if this is the ice edge and the ice is over here, you can't drive a ship over here, but you can drive one over here. So you want to predict that line. That tells you where you can drive your ships. There are serious errors in predicting where that edge is in August and September, when you really want to know it. Of course, you can predict it in March. It's right up against the coast. This is the open water season. You better figure that out. And here's a map of the errors, and I won't go into detail, but Canada's doing pretty well. These numbers down here say Canada's doing pretty well. The Norwegians are doing really great. We're not too bad. We're doing better than some of the Russians. This is the thing that we have to figure out. If you're going to navigate vessels in the Arctic and they have to skirt the ice, you better know where the ice is. It's a multi-billion-dollar question. So there's large ice edge errors. And the work that I've been doing recently, here's a paper that we did. We took observational data from the satellites, that's this picture here, from Russian drill stations where they drilled in the ice to measure how thick it is, from submarine data, that's the light gray dots, from aerial surveys, and we compared that with 8 of the best global models around the world. So the models are doing pretty good. They don't do a bad job, but what they do is they overestimate the thin ice. So you want to drive your vessel out there and you say, I need to know if the ice is less than a foot thick. The model says it's 2 feet thick. You say, well, I better not go. But the model's overestimated that, so you've just lost an opportunity. That's a bad error to have. There's underestimations of the thickest ice. So that means if there's big, thick ice in the Arctic someplace, maybe it's 3 meters thick, maybe it's 5 meters thick, but your forecast says it's half that, that's also a problem. That's also a problem because now you might say, well, you can drive a ship through there. It's only 3 feet thick, but it turns out to be 6. So these are the kinds of errors that we have to figure out and get them right before you tell ships where they can and cannot go. And you can see from this list of authors, this is an international team. So what are we going to do in the future? we have to establish this ice forecasting system. We got to have real-time ice and ocean observations. We've got to feed them into smart people who are working on this problem and continue to make it better and better and better, improve the short-term accuracy. What's it going to be like tomorrow? We all look at our thing and what's the Weather Channel say? Oh, today's going to be a nice day. Great, we go out and we do our stuff. We need that kind of stuff for all along the Arctic coastline. We need long-range predictions. Is next year going to be a really good shipping season? Can we push the boundaries of the open water season? When will sea ice freeze up and when will it break up? That tells us the edges of the navigational window. And we're looking at wave and wave ice interaction. That's kind of a sciencey question, but it basically says the more the Arctic opens up, the more winds can blow on that ocean that makes waves that can break up the ice around the edges. We need to establish protocols for search and rescue. Completely wide open question. How do you rescue people up in the Arctic if the nearest port is in Seattle or Nome and you've got a problem in Prudhoe? How are we going to do search and rescue? How are we going to save lives in a place where we're not even sure where the ice edge is right now? We need roads to deep water ports, as I've said, and we need to figure out how to supply power to this. Is it going to be carbon neutral? Are we going to go nuclear? Is there redundancy? Do we burn flared gas on the North Slope and build transmission lines for the interior? This is questions that we have to answer. So thank you for listening to me rant about the future of the Arctic Ocean and some of the things that I think are important. If there's questions, I'd be happy to address them. I'm delighted you came out here tonight on a beautiful Fairbanks summer evening. Thanks for your attention. I appreciate it.
We do have a question that came in from our online viewers, and they want to know, would freshwater runoff from Greenland melting ice disrupt the North Atlantic portion of the Gulf Stream?
That's a great question. So there is a circulation in the ocean. There's two kinds of circulation. The wind blows on the ocean and makes it move. There's another one that when cold water sinks in high latitudes, around Greenland, for example, and sinks to the bottom of the ocean, it sets up a circulation that moves globally. And think of yourself in a bathtub, right? Your foot hits the cold water and all of a sudden the bottom of the tub is cold. It's exactly like that, a little more complicated. This deep sinking sets up, let's just call it the Gulf Stream, to move north, to carry heat north. That makes Europe about 8 degrees warmer than it would normally be for that latitude. So if you live in Europe, you're really happy for this Gulf Stream and this deep water thermohaline circulation. So if there's deep water sinking around Greenland because it's so cold, and now you start melting Arctic ice is fresh. It floats on top. You can't make it heavy enough because it's fresh to sink to the bottom. It has to be salty to sink. So this circulation of sinking water and Gulf Stream going north gets braked, right? Like braking a car, it slows down. So if you live in Europe, a melting Arctic slows this circulation and you will actually cool. Their weather will get colder. So the answer to the person who wrote in is, this is a very serious problem regarding global climate and this background flow that moves heat around the planet. If you shut that down, it's a different ball game for climate on this planet. Without the oceans, the equator would be too hot and the poles would be too cold. Simple as that. Thanks for the question.
Yeah, I have a number of questions, but is there I missed the first part of the presentation, unfortunately, but is there a futuristic date that when you can almost navigate year-round through the Bering Straits?
There are a lot of futuristic dates. Some of the work I'm doing suggests maybe it's 2100. Some say earlier. So it depends on a whole lot of factors. But yes, given the trends that we see now, maybe 2100, maybe decades earlier or later, if we don't do any kind of course correction.
Another question now, Finland, Norway are pretty close to us. Of course, they're far away because we direct shops them, but it looks like we potentially can here pretty soon, huh? To be able to have shipping into those circumpolar countries.
Oh, yes, I am expecting and anticipating that if you are one of the global shippers, you're paying very close attention to when we know the shipping season will get regular. As I mentioned, there was a quote from a colleague in Canada who said it really hasn't increased as much as we might have expected because it's still not quite predictable. Yes, it will open up, but does it open up on, I'm making these dates up, May 15th, or will it be June 7th? And until you know that and can be reliable, shippers are reluctant to use those shipping lanes until this becomes pretty regular. Did I answer your question?
The different ships that you mentioned from different countries that are capable of breaking ice, how many of those are private industry created and private company operated?
I don't know the answer to that question. I think the ones I was showing here are all government owned and not private sector. I'd have to double check that. So I know that the US is looking at leasing private sector icebreakers from Canada and Finland and other countries. How available those are, I don't know. That's a good question. I can find that out. Good question.
A brief question that a lot of folks are wondering for the future on the northeast versus the northwest passage, and how that'll have effects on Alaska.
Well, if ships take the passage going along Russia, they doubtless will be charging for that. And if they come across Alaska, we'll be charging for that. So there's a huge economic incentive to say, please pay us, you use our side. Right now it's a little easier to go on that side for lots of reasons, but the route is shorter coming across if you're going London to the West Coast or something like that. So there will be economic incentives to use one place or the other. It also depends on how cheap is the fuel that you can buy. If we're shipping fuel to Nome that people are buying, of course you're going to want to go to the Russian side where they've trucked it in and it's half the price or something like that. So these are all things to consider, but it's economics that'll drive that.
You showed a graph of the ocean temperatures, and there was a decline of temperatures around the 1985 area, and there was another previous, maybe 10 years before that. Do we know why back at that period of time? Because that wasn't that long ago. And can we get back to that pattern if we know why that happened?
Those are great questions. When you lump all data together like that for a northern or southern hemisphere, it's kind of hard to tease out the exact reasons for that. It's certainly clear that, so some of my own work is to identify these natural cycles, and there are things like El Nino that are 5 to 7 years. There's this Arctic oscillation that is 5 to 12 years. There's an 80-year period, and all these things are ringing and interacting, just like the tides do. And you can have a super high tide because multiple tides have interacted. So I can't answer your question specifically, except to say that whenever the models and the observations diverge, we are trying to figure out that. But I'm not clear that there's any way to get back to this pre-industrial state unless we start to sequester and draw down the carbon, because that's really what's driving that. And a real consideration is if you warm the Arctic, the methane hydrates, that's frozen methane that's below the permafrost around the Arctic, deep under the ocean. If that starts to thaw because you've warmed the Arctic, now you've got episodic eruptions of methane coming out, and methane is a much, much more potent greenhouse gas. So that's like all of a sudden today you would really dial up the global warming signal. So there are things to be concerned about, and how we get back to these pre-industrial states. I'm not sure that it's possible, but I think we'll be geoengineering an awful lot of stuff in the future, trying to keep our planet habitable, maybe. I'm making it up, I'm guessing, who knows? I wish I had a good answer for you.
Thank you very much for this wonderful presentation. You've condensed a lot of history and a lot of science into something that we can understand.
Thank you.
My question is about Arctic policy generally. From the standpoint of the United States, as we're seeing all of this militarization in the Arctic, we're seeing an economic issue dealing with shipping commodities. We're seeing environmental issues. We're seeing indigenous people wanting to assert themselves, environmental groups that want to come and hug things up here. How ideally can we formulate an Arctic policy at a national level, and who represents the state of Alaska in this whole situation?
Well, I can answer that quite simply. No, not at all. That's how we go forward in the future to address these incredibly complex problems. And one of the hopes in giving a talk like this is to get us thinking and recognizing that we do need a forum where indigenous stakeholders and business people and economic drivers and environmentalists and just bring them all to the table and try to figure out how do we deal with those tough issues. I'm not sure that people can sit around a table and handle the geopolitics. That kind of happens at a different level. But the question of, are we going to allow ships in the Arctic because they might spill oil or things like that? Those are great questions that we as a society have to answer. And I don't know how that's going to turn out, because economic incentives tend to be so persistent that unless there's a strong reason not to do something sooner or later, you wind up drilling or doing something because economics drive it. I don't know how else to answer your question. I mean, how do you satisfy this huge range of stakeholders that you've just described? It means we have to talk to one another.
What about the state of Alaska having a position?
Well, I'm hoping our senators are thinking about that right now and asking smart people who have knowledge of these kinds of things to be at the table to represent our stakeholders. I'm a scientist. I deal with facts and data, and sometimes those scientific answers get shunted aside when you wind up making a decision. So I don't know. I don't know how we do this, except let's give it a shot, because we don't have any choice. Yeah, I mean, it's a tough question. You know it's a tough question. I don't know. I wish I had a pat answer.
Mark, one of your slides showed the estimated reserves of oil and gas under the ice. As the world is changing now, and many societies are moving away from oil and gas, I know the rare minerals will be important, but will that become less of an incentive to move quickly?
That's a great question. It's certainly, as a scientist, my hope that we move towards carbon neutral, but I'm not sure that means that we don't extract fossil fuels and make use of them, because while we can do better with our automobiles and our houses and our office buildings, I don't see any solution for fossil fuels fueling big pieces of equipment and things like that. You can't put a battery in a multi-ton vessel and get it to drive. So I think the pressure to extract those resources may diminish, but I think it will always be there. I don't think you can solve this carbon neutral problem, if that's the way you want to frame it, by trying to just say we won't use fossil fuels. I think we have to figure out how to use them better and smarter and be way more efficient. But I don't see that you can say, well, we're just not going to use them. They have to be part of this solution.
Okay, do we, one more question over here. Just a minute, wait for the microphone.
That's okay. Mark, what's your take on the strategic siting of a deepwater port facility at Nome? I mean, it is south of the Bering Strait, and then one thing you didn't mention was any sort of large vessel repair facility anywhere on the entire western coast or the Arctic coast.
It sure seems to me that if you say, let's start with Nome, and we go there and we learn a bunch of things and build it, then you better be thinking, actually now, where will the others be? And what's the best place? And I'm no expert in this field, but from the casual reading I've done, is there's no place that readily shouts out, I'm already deep. So now you're talking about dredging and doing those kinds of things that require massive engineering and continued attention to keep a deep water port deep. So this is a tough problem, and if it's unsolved, the traffic will go to the other side, as will the dollars. That's my take.
I guess so you have that illustration there of Alaska and the deepwater port in Nome, but you didn't have any, is there any deepwater ports on the Russian side that?
Yes, there are. I could have listed those. I have not. My perception is Russia is far more prepared for shipping all along their coast than we are as in the U.S. or as Alaska.
Any other questions here?
Mark, why do you suppose the sea ice is still attached to the north side of the Canadian Islands?
It's for two reasons. The currents want to move it that way. The water comes in through essentially Bering Strait, and it moves towards the Canadian Archipelago and Greenland, and it just carries the sea ice. And the winds there want to do the same thing. So the thickest ice in the Arctic, historically and even now, is all wedged up against that side of the Arctic Ocean.
So it's the Arctic gyre pushing it against it?
It's the transpolar drift, we might call it, where that drift pattern of the Fram is the background reasoning for that current that's just wedging it up against there and damming that whole place, which is why Perry could not get through, because he got to this point where ice is super thick, and if you're in a wooden sailing vessel, you kind of turn back.
Maybe lastly, University of Alaska has focused on this for decades. Will we be part of tomorrow in making these kind of decisions and aiding the United States in doing this?
Well, I sure hope so. So how do you do that? You fund a university so it can do the research that's required to answer these questions. And you don't neglect repairing your buildings. You give it a budget that makes it one of the world-class universities, and you say, this is what we're going to do, and you don't neglect it, in my opinion. But obviously, I have a vested interest in intelligent decision-making and a smart academic community.
Thank you.
Thanks, everybody, for coming. Thanks for that.